Galvani. Robert Davidson, a Scottish chemist, built the world's first full-size electric locomotive in 1842, a battery-powered machine he named Galvani. It stretched about 16 feet long, weighed roughly 7 tons, and managed a top speed of 4 miles per hour on the Edinburgh to Glasgow Railway, drawing current from 76 zinc acid cells that could not be recharged. Running on disposable zinc cost roughly 40 times more than burning coal, and railway workers who feared for their jobs smashed Galvani to pieces in its shed. The real dawn of electric traction came 37 years later when Werner von Siemens unveiled a generator-powered locomotive at the 1879 Berlin Trade Exhibition. A 3-horsepower series-wound motor drew 150 volts DC through a center third rail, pulling 3 open cars at 8 miles per hour around a short demonstration loop. Over 4 months, it carried roughly 90,000 passengers without a single incident. Siemens followed with the world's first electric tram line at Lichterfelde in 1881, and by 1895, the Baltimore and Ohio Railroad had electrified the Baltimore Belt Line, the first mainline electrification in America, running 600-volt DC overhead catenary with General Electric steeple cab locomotives rated at 360 horsepower. That original 1879 Siemens locomotive still exists, preserved in the Deutsches Museum in Munich, the oldest electric locomotive on Earth. DC Electric Locomotive. Direct current was the first system to move from experiment to mainline service. And for a simple reason, early engineers understood DC motors far better than anything alternating current could offer. A DC series wound motor delivers enormous starting torque, exactly what a heavy train needs to get moving from a dead stop. The Baltimore and Ohio's 1895 Beltline ran on 600-volt DC overhead. London City and South London Railway had already become the world's first electric underground in 1890, powered by 500-volt DC. Third rail systems soon became the standard for subways and commuter lines. London Underground adopted a 4-rail arrangement combining positive 420 volts and negative 210 volts for a total of 630 volts. Higher voltage DC overhead at 1,500 or 3,000 volts powered main lines across the Netherlands, Belgium, Italy, and parts of France. The New York Central S motor of 1904, built by General Electric for Grand Central Terminal service, weighed 200,000 pounds, produced 2,200 horsepower from 660-volt DC third rail, and hauled express passenger trains at 70 miles per hour. But the limitation of DC is physics itself. Low voltage means high current, heavy copper conductors, and substations spaced barely 1.5 miles apart. Third rail DC also caps practical speed, near 100 miles per hour. Every high-speed line on Earth runs on AC instead, a verdict that speaks for itself. AC Electric Locomotive. Alternating current won the main line because of one elegant equation: power equals voltage times current. Raise the voltage, and you can slash the current, which means thinner wires, lighter infrastructure, and substations spaced every 30 miles instead of every 1.5. The first standard gauge AC mainline was the Bergdorf to Thun line in Switzerland, opened in 1899 on 3-phase 750-volt 40 Hz current, requiring 2 overhead wires plus the running rail. 3-phase motors offered regenerative braking on mountain grades, but the double catenary made junctions impossibly complex. Hungarian engineer Kalman Kando, often called the father of the electric train, developed 3-phase traction motors at the Gans Works in 1894 and electrified Italy's Valtellina line in 1902, 66 miles through alpine tunnels. Single-phase AC proved far more practical. One overhead wire feeding an onboard transformer became the global standard. 25,000 volts at 50 Hz for new mainline construction, 15,000 volts at 16.7 Hz across Germany, Austria, Switzerland, and Scandinavia. 3-phase traction survives today only on a handful of Swiss mountain rack railways, relics of a bold idea that physics outgrew. GG1. The Pennsylvania Railroad GG1 is the most iconic electric locomotive in American history. Industrial designer Raymond Loewy gave it a seamless welded body and gold pinstripe livery that turned an engineering project into a work of art. General Electric and PRR's Altoona Works built 139 GG1s between 1934 and 1943. Each stretched 79 feet long, weighed 475,000 pounds, drew 11,000 volts, 25 hertz AC from overhead catenary, and delivered 4,620 horsepower continuously through 12 traction motors, with burst peaks near 9,000 horsepower. Top speed was 100 miles per hour. The GG1 hauled everything from 20-car passenger limiteds to wartime freight on the Northeast Corridor between New York and Washington. One pulled President Franklin Roosevelt's funeral train from Warm Springs to Washington in April 1945. On January 15, 1953, GG1 number 4876 crashed through the floor of Washington Union Station at 80 miles per hour after a brake failure and was repaired and returned to service. The class served nearly 50 years. New Jersey Transit retired the last in October 1983. 16 survive in preservation, but none will ever run again. The GG1 was born too early for modern power electronics and too late for the steam age, but nothing on rails ever looked better doing the job. Electric Multiple Unit. The Electric Multiple Unit, or EMU, is not a locomotive at all, and that is exactly the point. Instead of concentrating all power in one heavy machine at the front of a train, an EMU distributes traction motors under multiple cars throughout the consist. American engineer Frank Sprague invented multiple unit control in the 1890s, and Liverpool's overhead railway ran early two-car EMUs by 1893. The advantages are decisive. More powered axles gripping the rail means faster acceleration and better adhesion. Distributed weight reduces axle loads and track wear. Regenerative braking across the entire train recovers energy that a single locomotive would waste as heat. And eliminating the dead weight of an unpowered locomotive frees space for passengers. The trade-off is flexibility. An EMU is a fixed formation, and one failed car can sideline the whole set. But this single concept is the foundation of virtually all modern commuter and most high-speed rail on Earth. Japan's Shinkansen bullet trains are EMUs. Germany's ICE-3 is an EMU. London's Elizabeth Line trains are EMUs. When engineers in the 1960s asked how to build a train that could justify a 3-minute headway on the busiest rail corridor in Asia, the locomotive was the first thing they threw away. Shunting and mining electric. Not every electric locomotive is built for speed. Shunters, called switchers in North America, are small, slow, high-tractive effort machines that assemble and disassemble trains in rail yards. Electric shunters produce zero local emissions and run far quieter than diesels, making them ideal for indoor freight terminals and urban yards. But the oldest and most critical use of electric traction in confined spaces is underground mining. Electric mine locomotives dominated underground haulage from the 1890s through the 1960s because they eliminated the fire and ventilation hazards of steam and combustion engines in tunnels where breathable air is scarce and explosive gas is common. Siemens and Halske had a storage battery mine locomotive working at Gelsenkirchen by 1904. The United States standardized on 250 volts DC for underground safety by 1914. Both trolley wire and battery types saw service, some weighing under 5 tons and others exceeding 30. In modern yards, Toshiba has delivered lithium-ion hybrid shunters to JR Freight in Japan, with permanent magnet motors producing 670 horsepower. Union Pacific began testing diesel battery hybrid switchers in 2024, expected to cut yard fuel use by up to 80%. High-speed electric train. No other category of electric traction reshaped transportation like high-speed rail. Japan's Tokaido Shinkansen opened on October 1, 1964. The first railway designed for speeds above 130 miles per hour. The original Series 0 ran at 130 miles per hour on 25,000-volt 60 Hz AC with traction motors distributed across every car. During peak hours, 16 trains per hour depart in each direction at a 3-minute headway. Each 16 cars set seating 1,323 passengers. The Tokaido line alone has carried over 6.5 billion passengers since opening, with 0 fatalities from train accidents. France's TGV entered service in 1981, running commercially at 199 miles per hour. Germany's ICE launched on June 2, 1991. Its experimental predecessor ICE-5 hit 253 miles per hour in 1988. China's CR-400 Foxing entered service in 2017 at 218 miles per hour, with the next-generation CR-450 targeting 249 miles per hour. The absolute speed record for a train on wheels belongs to a modified TGV-designated V150, 357 miles per hour, on April 3, 2007, powered by 26,000 horsepower on catenary voltage, boosted to 31,000 volts with oversized wheels. That record will almost certainly never fall in scheduled service. The power needed to push through air rises with the cube of speed, double the speed, and you need 8 times the energy. Battery electric and Maglev. The two extremes of electric traction's future could not look more different. The Wabtec FLX drive is the world's first 100% battery-powered heavy-haul mainline locomotive. Its 2021 pilot on BNSF in California, weighing 430,000 pounds and packing 18,000 lithium-ion cells, cut fuel consumption by over 11% across a full train, saving roughly 6,200 gallons of diesel over 13,320 miles. The production unit for Australia's Roy Hill Iron Ore Railway carries 7 megawatt-hours from 36,288 cells and recharges through regenerative braking on the 214-mile loaded downhill run from mine to port. The hard limit is energy density. The first-generation FLX drive ran only 30 to 40 minutes at full power standalone. At the opposite extreme sits magnetic levitation. Japan's L0 series set the absolute rail speed record at 375 miles per hour on April 21, 2015, floating 4 inches above the guideway on superconducting magnets, cooled to negative 452 degrees Fahrenheit. The only high-speed commercial maglev on Earth is the Shanghai Trans Rapid, 19 miles from airport to city, in 8 minutes at 268 miles per hour. But maglev cannot share existing track, and dedicated guideway runs roughly $70 million per mile. Nearly 2 centuries after a mob smashed Galvani in its shed, the electric locomotive did not just survive, it became the fastest, cleanest, most efficient way humanity moves overland. Multi-system locomotive. Europe's rail network is a patchwork of 4 incompatible electrification standards: 1,500-volt DC, 3,000-volt DC, 15,000-volt 16.7 Hz AC, and 25,000-volt 50 Hz AC, built over a century of national decisions that nobody ever coordinated. For decades, international trains stopped at every frontier to swap locomotives. The multi-system locomotive solved that problem by putting the brains on board. Modern power electronics detect which voltage and frequency the overhead wire is feeding, then transform, rectify, and invert the power accordingly, all automatically. The leading example is the Siemens Vectron, a modular 4-axle locomotive configurable for all 4 European systems, producing up to 8,600 horsepower at speeds up to 125 miles per hour. Siemens has delivered well over 500 Vectrons across Europe. Its predecessor, the ES64U4, set the locomotive speed record at 222 miles per hour on September 2, 2006, the fastest a single electric locomotive has ever traveled anywhere in the world. The multi-system concept proves a simple point. In the 21st century, it is cheaper to put intelligence in the locomotive than to rewire an entire continent. Thanks so much for watching. If you enjoyed it, smash that like button, share it around, and I'll catch you in the next one.